So at this point in the development of quantum mechanics, we're in the late 1800s, early 1900s, and people are doing all kinds of experiments. People are doing experiments on these small particles that come from cathode rays, and that people that we didn't know about previously, basically electrons. We haven't yet discovered the neutron and proton in the scheme of things. To get the dates right, the Millikan oil drop experiment, I got that a little wrong. He started in 1909, and he published his first results in 1909, and then continued the experiment to 1910. And then it was 1911 that Rutherford discovered the nucleus, which we haven't gotten to yet. We'll get to that later. So I just got the dates a little wrong. But we're talking about 1897, discovery of the electron, to 1911, and Einstein was right in the middle there in 1905, where he published this idea of quantum mechanics. And it's these experiments that came both before Einstein and after Einstein that helped to solidify this concept of quantum mechanics that when Einstein first proposed it was not well accepted. Got to keep that in mind. Wasn't well accepted until the 20s when all these experiments really confirmed quantum mechanics must be true. So where are we? 1897, the electron is discovered. There are kinks in the wall, right? Cracks in the wall. There's experiments that aren't understood. We have now, with Millikan in 1909, we have quantized charge, and we have also measured the mass of the electron since Thomson measured Q over m and Millikan measured Q. Therefore, we now know m, the mass of this electron, and it's far smaller than any other particle we have ever measured. So we know we have this fundamental particle called the electron. And we've now measured all its properties. Now let's move on to an experiment. Move on to one of these kinks or cracks in the wall, things that weren't understood circa 1900 before Einstein's proposal, and that's line spectra. In 1888, Johannes Rydberg came up with an empirical formula to describe something that wasn't understood. So maybe this is late 1800s. Again, it's late 1800s. And what wasn't well understood is the concept of line spectra. And what wasn't understood about it is it's another example of quantization, of apparent quantization. And while an empirical formula came up to describe line spectra, it wasn't understood until quantum mechanics came about what was quantized, or that something was actually quantized. So what's the concept of line spectra? The concept of line spectra is something that you've probably seen before, which is that, for example, if you take a dilute gas, or a dilute gas or a pure gas, and you put some energy into it, that gas will glow, like a neon sign. You've seen those before. The gas will glow, but if you look at the spectrum of that, what you'll see is that it doesn't emit white light. It doesn't emit light in a continuous spectrum. It only emits individual colors. In other words, you get a discrete spectrum out of an excited gas, and that no two elements have the same spectrum. So let me show you some examples of this. So now, of course, remember 1888 when Rydberg first wrote down 1888, Rydberg wrote down the empirical, right, the observed results. This is about the time when cathode ray tubes started being used. They're basically evacuated glass cylinders. So it's the first time we're able to really look at pure gases, because what you could do is you could evacuate a glass cylinder and then just put in a pure gas of some sort. So, and a dilute gas is really what you need to do in order to do this experiment. So let's say, and so what I'm showing here really is just a glass cylinder. And if I was in a lab, I would be holding these glass cylinders in my hand. They're sort of slightly larger than a pen. A glass cylinder filled with a gas. And all you have to do is put, a voltage difference. We're always using voltage differences. Put a voltage across the gas. And so you're now exciting the gas, and the gas will emit light. I'll show you real examples of these soon, but the gas emits light. It emits light, and it looks like it's glowing red or blue or yellow. But if you then send that to us through a spectrum analyzer, And today we've got these machines that are spectrum analyzers, but really you can just send it through a diffraction grating, right? So the same thing that we used to do interference with a light source, and you send it through a bunch of slits. And what that does is it actually separates out the colors. And so you can send it through a diffraction grating and project the results on a screen. I have to draw a picture here. So now I got rid of the argon tube because that was in the way. So helium tube, we're exciting it. It emits light. We send it through a diffraction grating. A diffraction grating is just it's something with a bunch of slits in it, just a bunch of slits, literally slits in it, that makes the light interfere. And what that interference does, it is actually just interference that separates out the colors. Sort of like a prism separates out colors for white light, but not the same process. But that's what's going on, is we're separating out the colors. And on a screen, you're going to see some pattern. And I didn't draw the correct pattern for helium. But if instead we replace the helium with argon, we're going to see a different pattern. And if we replace that with neon, we're going to see a different pattern. And those patterns are both unique, but what's more important, or as important, is the fact that they're discrete. It's not a continuum. White light, when you separate it through a diffraction grating, or through a prism, you get a rainbow, which is a continuum, Roy G. Biv. You get all the colors. But with line spectra, we're seeing discrete lines. We're not seeing all the colors. Some colors are missing. And again, the signature of a gas is unique to that gas. Helium has a different spectrum than argon, than neon, than any other gas. So this is what line spectra are. So we don't understand in 1888 or in 1905 why we're getting this, but Rydberg is able to write down an empirical equation which allows you to calculate what colors you might get out. I'm going to cut to some real demonstrations of line spectra and then come back and describe the Rydberg equation.